Hi everyone, my name is Oleg Zaytsev. I'm a software engineer from Grafana Labs Mimir squad, and today I want to share you some of the challenges we had to overcome in order to handle 1 billion of active series at Grafana Mimir. Last year we had a business case to run Grafana Mimir with 1 billion active series within a single tenant. Since then we have made substantial improvements to Grafana Mimir, so this talk is only some subset of the features we have. Before we start, I want to introduce you to Grafana Mimir. Mimir is an open source distributed time series database for Prometheus. It provides high availability, horizontal scalability, real multi-tenancy, durable storage, and fast query performance. We also ship Mimir with a rich set of production-grade Grafana dashboards, Prometheus alerts, and runbooks. You can use them to monitor your Mimir installation from day zero, just like we do at Grafana Cloud. Mimir doesn't replace Prometheus, but instead it just extends it. When using Mimir, you keep running Prometheus configured to scrape metrics from your applications and infrastructure, and remote write these metrics to Grafana Mimir. Alternatively, you can use Grafana Agent or Prometheus Agent to send data directly. Then you just configure Grafana to query metrics from Mimir, leveraging on Mimir's scalability and performance optimizations. I also want to give you a quick overview of Mimir's architecture to make understanding of the presented challenges easier. On the right path, Prometheus, or Grafana Agent, writes metrics to the distributor, which is responsible for sharding and replicating metrics across the ingesters. The ingesters keep the most recent metrics data points in memory and local disk, and periodically upload these metrics to the object storage. On the read path, Grafana sends query requests to query frontend, which is responsible for accelerating the query execution. I will cover the query acceleration techniques more in details later on. Queries are executed by a pool of queryers, which fetch the most recent data from ingesters and older data from the store gateways. The store gateway is responsible for fetching the actual data from the object storage, and it provides an abstraction layer for different storage providers like GCS or S3. The compactor is a component which asynchronously deduplicates and compacts blocks periodically uploaded by the ingester to the object storage. I will also cover the compact more in details later on. When alerting rule fires, the event is sent to the alert manager, which is responsible for delivering notification through the configured receivers like by email, Slack, PagerDuty, Grafana call, and many more. Mimir's alert manager is based on Prometheus alert manager, and it adds multi-tenancy on top of it. So back to the original topic. What's a billion active series? A series is a set of samples observed at certain timestamps. Each series is identified by a set of labels. In this example, we have two series of metrics named foo with different label values, and we also have a single series of metrics named ba. These three series are active series, since they had samples in the last 20 minutes. The orange series on the left doesn't have any samples in the last 20 minutes, so it's not considered an active series. So today we are talking about ingesting 1 billion active series that received at least one sample in the last 20 minutes. And by the way, I'm talking about it in terms of US billions. I'm saying that because Spanish billion is a million of millions, just like the British one was until not so long ago. That creates me a lot of confusion when I'm thinking about the scale. My girlfriend told me that I should use GIFs in my presentation, so I just added this slide to use a GIF. And scale. I've spent a lot of time trying to find a good example of the scale of this number. And I think that the best way is just to take Prometheus instance itself as an example. In my home lab, it exposes 1,000 metrics. So a billion active series would be like scraping metrics from 1 million Prometheus instances. In order to be able to ingest and query such a big volume of data, we had to tackle multiple challenges, like ingester operation bottlenecks, compactor throughput, block index size limitation, high cardinality queries, TSDB matches performance, slow rollouts, and hash ring performance issues. You can also read about them in the blog post that I'm going to link at the end of the presentation. So just like the architecture interview, let's start with the write path. As I explained before, the ingesters are the stateful components of Mimir in charge of storing metrics in memory and disk. In our experiment, we simulated 20-second scrape interval, which meant that our ingesters were receiving 50 million samples per second. This number has to be multiplied by the 3x replication factor later. Prometheus TSDB that Mimir uses stores samples in a data structure called a chunk. Each chunk holds by default 120 samples each, which is the optimum balance between getting the best compression ratio of the samples without getting too long chunks, because those are more expensive to read later. With 120 samples in each chunk and 20-second scrape interval, a chunk gets full every 40 minutes and has to be flushed to disk. This meant that in our test, every 40 minutes, each one of the 600 ingesters was writing to disk around 7 gigabytes of data within a few seconds interval. Since the chunk writing operation was a blocking Prometheus TSDB operation, it meant that we observed very, very slow requests every 40 minutes. So in order to solve this, we added 2 improvements. First, we introduced a jitter to the chunk size. This would prevent them from being flushed to disk at exactly the same time. The jitter depends on the series hash, and to make sure that every ingester replica chooses the same jitter for the same series. We also added a queue-based approach to the chunk writing. So chunk writing would no longer be blocking for the subsequent writes. As a result, the 99th percentile of the write latencies decreased from 45 to 3 seconds, which was within the objective we set of 10 seconds to ourselves. And after ingesting all that data, Mimir must then compact it at the same rate. The original Grafana Enterprise Metrics compactor could only concurrently compact blocks of different time ranges, which meant that all the ingested data from given time range was compacted by a single thread. In other words, a single thread had to compact 150 million samples per second in order to keep up with the ingestion rate. This caused the compactor to fall behind and compact the data slower than it was ingested, leading to lots of uncompacted blocks in the storage, which in turn decreased the performance of the read path. As we approached the billion active series, it wasn't just about the speed anymore. Prometheus TSDB blocks have a 64 gigabytes index size limitation, which comes from series being addressed with a 32 bytes unsynced integer, and they are aligned to 16 bytes boundaries. Having this many series meant that after a long running compaction, it would fail because the output block can be built. We could have modified the TSDB format we used to address that, but we want to keep being compatible with the original Prometheus TSDB, so we had to go a different way. In order to overcome these limitations, we created a new compactor called the split and merge compactor. Let's see how it works. This compactor has a configurable amount of output shards. For this example, we'll use 2 shards just to simplify the diagram. Let's assume we have 4 ingesters producing 1 block each. Note that each ingested series is replicated across 3 different ingesters in this form. First, we run the split compactor stage. At this stage, the compactor instance takes the portion of all blocks, compacts it, and produces as many blocks as shards were configured. Each shard contains only the series which hash belongs to that shard. Then the merge compactor takes the split blocks for each shard and merges them into a single block. Note that merging 2 blocks with series from a given shard produces a block with the same shard. This way we can parallelize the compaction of a single time frame. And we can make the block smaller by just increasing the number of shards, overcoming the index header size limitations mentioned previously. And we can drastically increase the compaction speed. The block size doesn't decrease linearly with the number of shards, because sharding on series hash ends up putting different series of same metrics into different blocks, having duplication of the label names and values across multiple blocks. Like for instance, the job label or the metric name label name are most likely present in every block, but since the index is just 10% of the block size, we are happy with the results. And These are just some of the optimizations we did on the write path, but we also have to do it on the read path. Prometheus PromQL engine that Mimir uses is single-threaded, which means that the duration of each query depends on the length of the time window and the number of series that there is in the storage. This means that you have to scale Prometheus PromQL engine vertically in terms of memory and CPU core performance. And sometimes the question isn't when it will return results. Sometimes it's just will it return or will it crash instead? You all know Prometheus probably. So in order to make it scale, Mimir splits the time range queries into smaller range queries by default, caching them where possible. This basically means that once you've queried a 30-day range query, the next query some moments later will only reevaluate the last few minutes of new data, relying on the cached results for the rest of the range. When the results are not cached, the subqueries time range are aligned to the block sizes to improve the resource utilization and are executed concurrently to improve the query speed. When the result is not cached, with a billion of active series in the storage, there is a lot of data to retrieve. So we've implemented series hash-based sharding. We call it just query sharding internally. Each query is split into smaller cardinality queries, executed concurrently, and then the results are merged back using an appropriate function. For the example on the screen, when you run a sum over 8 of some metric selector, that can be evaluated separately for each shard of the series, and then we can just sum the results. The number of shards is dynamically calculated up to a given limit to optimize the resource utilization. And you can notice that not all the queries can be sharded entirely, like histogram compile cannot be sharded because you have to calculate it at once. But they can take advantage from query sharding because the sum inside of the histogram compile can be sharded. At the moment, 60% of all our customer queries running on Grafana Cloud are sharded, and we are working to support query sharding for more query types. On average, we observe a 10x reduction in execution time for high cardinality and CPU-intensive queries. For example, in the screenshot, the high cardinality query running on the same Mimir cluster with and without query sharding enabled, the execution time was reduced from 40 seconds to 4, which is like a long time staring at an empty dashboard. And it's not only about speed, so it's also about the resources. Even though the sum of all executed work is slightly bigger because now we have to post-aggregate again, this increases negligible compared to the benefits of distributing the load across more smaller subqueries. We are so happy with this load distribution that since Mimir 2.1, we support the recording rules evaluation to use an external query evaluator, and we reuse the sharded query frontend path for it, reducing the number of memory speaks in the rulers. I also want to note how well the different improvements work together. Since both query sharding and split and merge compactor use the same series hashing algorithm, we can shortcut query path because we know beforehand whether a given subquery shard does not have any data in a given block shard. This works both ways when there are more subquery shards or more block shards. Of course, even here there's a room for optimization. When we have a set of matchers, we can't calculate which series belong to a given shard before retrieving all their labels. Whenever the number of query shards is higher than the number of block shards, which is a quite common situation like you can see on the screenshot, the queries end up asking store gateway for multiple shards of the same series. In practice, this means that we end up having multiple Go routines within the same store gateway calculating which series match that same set of matchers at the same time. In order to reduce the amount of duplicated work, we added a promise-based approach and deduplicating the implied queries for the same matchers. Plus, we cache the results in memcache so we can reuse the results from different instances. We also upstreamed this change to Prometheus with an in-memory-based cache because, surprise, people are querying the same metrics all the time, so you can just cache the matchers. In our experience on Grafana Cloud, most most of the time, the hit rate of this cache is around 100%. So it's awesome because we do this thousands of times per second. And caching matches is great, but there's no limit to developers' creativity when it comes to writing queries. So we still have to evaluate matches from time to time. Prometheus does a good job trying to optimize regular expressions when they represent a trivial set of values. For example, in this, regular expression would only look up for 2 label values in storage, because that's much cheaper than checking each one of the existing label values and running the regular expression on top of them. However, as I said, there's no limit to developers' creativity, so sometimes we just try to make the regular expression shorter, and we force Prometheus to run the regular expression on all the label values present in the storage. Turns out we are not so creative when we run the regular expressions, and most of the time we do the same ones. We change the code so it would generate a finite amount of values from a regular expression when it's possible. So in the previous example, we still wouldn't need to scan all the label values. Sometimes it's not possible to generate a finite amount of label values, or like a bounded, decent amount of values. Like in .wildcard general expression, we can just merge any string. Or we still optimize some of them, like looking for a substring or checking some specific features. We were able to save up to 90% of CPU time on these common cases, according to our benchmarks. We haven't spin these improvements to Prometheus yet, but it's definitely in our plans. And it's not all about throughput of the application itself. We also made improvement to how we deploy and operate it. One of the issues we encountered were the really slow rollouts of the ingesters and store gateways. As I mentioned before, ingesters hold recently written series, each ingester holding one of the 3 replicas of a given write. We want to keep redundancy at all times, so when we are rolling a new version, we have to be careful not to take down more than one instance holding one of those 3 copies of the series. Kubernetes doesn't know about the distribution of the series, so what we did in the past was rolling out one ingester replica at a time. Considering a 10 minutes restart as an example, because each ingester has to replay all the write-ahead log, that would mean that we would have rollouts lasting for 100 hours or 4 days, so it doesn't really scale. In order to optimize that, we made the multi-zone rollouts as the default ingester and store gateway deployment option, even when all the zones are deployed in the same availability zone of your infrastructure provider. Once the ingesters are working in a multi-zone configuration, each zone holds one replica of given series. So now we can roll out an entire zone at the same time without losing redundancy. We leverage on another component we made open source called rollout operator to coordinate those restarts. In practice, we don't restart entire zone at once. We do it in batches of 40 ingesters at a time, which gives us enough balance between speed, confidence, and resource utilization. We don't want to kill the nodes just by restarting 100 ingesters. And hash ring in Mimir. This is the last thing, but not the least. Mimir uses hash rings to share work across multiple components, like the series replication across the ingesters. A hash ring is a data structure shared across the Mimir replicas using a key value storage, and we currently support console, etcd, and member list. Since the operation, so when using console or etcd, the entire hash ring is stored in a single key, and every instance periodically updates it with a timestamp using a compare and swap operation. Since those operations are mutually exclusive, there's a limit on how much you can scale, defined by the performance of your key value storage backend. And we hit that limit with our 1 billion active series test, because we were running 1,500 replicas of different services hitting the same backend. Member list is a gossip protocol that overcomes this limitation, and this is now the recommended way to run Mimir. Instead of performing atomic compare and swear operations that are immediately available on all nodes, member list just shares the changes with some instances being eventually available everywhere. However, when we switched to member list in our test, we found out that 1,500 replicas of all microservice components each replica was using between 1.5 and 2 cores just to propagate the changes using member list. So we investigated, profiled, benchmarked all the related code, and we came up with a set of changes that drastically reduced the TPU utilization. After weeks of making improvements, we were able to reduce the CPU load for member list operation by like 90%. In the screenshot, you can see one of those improvements being deployed on the distributors and queries. So what's next? We are drafting a release candidate this week that includes backfill API to upload entire Prometheus blocks, and as well as the out-of-order sample suggestion. We are very excited about the out-of-order sample suggestion. Ooh. It is especially interesting for customers who use Kafka to queue the writes because they arrive in different order. And it will also enable us to properly support Graphite and Datadog metric format ingestion, which we should be open sourcing later this year. And we obviously are doing much more, but I want to especially mention the efforts we are doing making it easier to operate Mimir. We are adding lots of documentation, we are improving the Helm charts, and we are adding actionable errors with runbooks, etc. And I didn't want to start with this because it was supposed to be a serious talk, but I'm pretty sure that many of you have been thinking about the Mimi, like there's a Mimir, then it's 2 Mimirs. Yeah, I want to use this slide because I often say Mimir, but the proper pronunciation is Mimir, just like the baby talk for sleeping in Spanish. And that's all. I hope you enjoyed the talk, and I'm open for questions. Otherwise, you can find us inside.
We've got time for any questions here. Any questions? We're all hungry for lunch. How are you hungry for lunch? This guy's had like 10 donuts. I'm not going to ask. Oh, God, that's a big number. We're not even going to say it for the stream. People on the stream should not know the number of donuts that you've had. All right, let's do one more round of applause. Thank you so much.